Hello, and welcome to this video series on algorithms. This is part 9 of Module 4 on greedy algorithms. In this section, we will study the minimized maximal lateness problem. Recall the interval scheduling problem from the previous section. In that problem, we manage a single-threaded server and aim to maximize the number of jobs executed. The constraint is that no two accepted jobs overlap in time. We now consider a different scheduling problem. Again, we are given a set of job requests. This time, all jobs must be executed. We are free to choose the execution order. Our goal is fairness. No job should miss its deadline by too much. We now give a formal definition of the problem. As in interval scheduling, we assume a single-threaded server that can execute only one job at a time. All jobs must be executed without preemption. We are given a set of n jobs I. Each job I has a processing time Pi and a deadline Di. The goal is to determine the execution order of the jobs. In other words, we assign a start time Si to each job I. In this case, job I finishes at time Fi equals Si plus Pi. If Fi is larger than Di, the job has a lateness Li equals Fi minus Di. Otherwise, the lateness is 0. To ensure fairness, we seek a schedule that minimizes the maximal lateness over all jobs. This problem is called the minimized maximal lateness scheduling problem. Consider a toy example with 4 jobs A, B, C, and D. One simple schedule is to execute the jobs sequentially. We start job A at time 0. Its processing time is PA equals 3. So it finishes at time 3. Since its deadline DA equals 4, its lateness is 0. Next, we start job B at time 3. Because PB equals 2, job B finishes at time 5. Its deadline is DB equals 7. So its lateness is also 0. We then start job C at time 5, and it finishes at time 9. Because job C's deadline is DC equals 6, its lateness is 3. Finally, we start job D at time 9, and it finishes at time 10. With a deadline DD equals 5, its lateness is 5. The maximal lateness in this schedule is therefore 5, which occurs for job D. From this example, we see that job D causes the maximal lateness because it is executed last, even though it has an earlier deadline than some other jobs. This suggests a simple improvement. Schedule jobs with earlier deadlines first. This intuition leads to a greedy strategy called earliest deadline first. Under this strategy, we give priority to more urgent jobs with earlier deadlines. Following this intuition, we can use an alternative schedule, A, D, C, B. We execute job A at time 0, job D at time 3, job C at time 4, and job B at time 8. Under this schedule, the maximal lateness is 3, which is smaller than 5 in the original schedule. The pseudocode describes the greedy algorithm. In line 2, we sort all jobs by increasing deadline. In line 3, we initialize a variable time to 0 to track the current time. The loop starting at line 4 processes the jobs in this order. In line 5, we update time to the finish time of the current job. In line 6, we compute the lateness of that job. Finally, in line 7, we return the maximal lateness over all jobs. Next, we prove the correctness of this greedy algorithm. We need to show that it minimizes the maximal lateness among all schedules. We use the same proof approach as in interval scheduling. Let A be the schedule produced by the greedy algorithm, and let O be an optimal schedule. We will show that A achieves the same maximal lateness as O. First, we prove proposition 1. There exists an optimal schedule with no idle time. Assume an optimal schedule has some idle time. We can eliminate each idle interval by shifting all later jobs earlier by the length of the idle time. This shift does not delay any job. It can only make finish times earlier. Therefore, no job's lateness increases, and the maximal lateness does not increase. The resulting schedule is still optimal and has no idle time. Hence, there exists an optimal schedule with no idle time. Next, we define an inversion. An inversion occurs when a job with the earlier deadline is scheduled after a job with a later deadline. For example, job A has deadline 4, and job B has deadline 7. If B is executed before A, then the schedule contains an inversion. The schedule produced by the earliest deadline first strategy has no inversions. Note that the definition of an inversion does not require the two jobs to be adjacent in the schedule. In proposition 2, we show that any non-adjacent inversion can be removed using a sequence of adjacent swaps. This idea is similar to bubble sort. Bubble sort eliminates all inversions using only adjacent swaps. And the same argument applies here. In proposition 3, we claim that there exists an optimal schedule with no idle time and no inversions. By proposition 1, we already know that an optimal schedule with no idle time exists. We now focus on eliminating inversions. Let O be an optimal schedule with no idle time, but with some inversions. By proposition 2, all inversions in O can be removed by repeatedly swapping adjacent inverted job pairs. This process produces an inversion-free schedule. We must show that swapping an adjacent inversion does not increase the maximal lateness. Consider two consecutive jobs, I and J, that form an adjacent inversion. That is, dI is less than or equal to dj, but j is scheduled before I. Because the schedule has no idle time, I and j run back to back. To remove this inversion, we swap jobs I and j. Let Si and Fi be job i's start and finish time before the swap, and s prime I, f prime I after the swap. Define Sj, Fj, and S prime j, F prime j similarly. After swapping the two jobs, job I starts earlier, so its finish time cannot increase. Therefore, I's lateness does not increase. For job J, it now finishes at the old finish time of I. So we have F prime j equals Fi. Its new lateness, L prime j, equals F prime j minus dj equals Fi minus dj. Since di is less than or equal to dj, we have job j's lateness equals to Fi minus dj and less than or equal to Fi minus di, which is exactly job i's lateness before the swap. So, after the swap, neither job exceeds the original maximal lateness. Therefore, we can repeatedly swap adjacent inversions without increasing the maximal lateness, transforming O into an inversion-free optimal schedule. Combining this with proposition 1, there exists an optimal schedule with no idle time and no inversions. Next, we prove proposition 4. All schedules with no idle time and no inversions have the same maximal lateness. This matters because multiple jobs may share the same deadline. This can produce many inversion-free schedules, depending on how ties are broken. In any schedule with no inversions, jobs are ordered by non-decreasing deadlines. Therefore, all jobs with the same deadline D must appear consecutively as a block. Because there's no idle time, the start time of this block is fixed. The total processing time of this block is also fixed. So, the finish time of the last job in the block is the same in every such schedule, regardless of the internal order of jobs within the block. Since every job in the block has the same deadline D, the maximal lateness among these jobs depends only on the latest finish time in the block, which is identical across schedules. The only differences between inversion-free schedules are tie breaks with equal deadline blocks. Those tie breaks do not change any block's final completion time, so they do not change the overall maximal lateness. Hence, all schedules with no inversions and no idle time have the same maximal lateness. We can now prove the correctness of the greedy algorithm. By proposition 3, there exists an optimal schedule with no idle time and no inversions. By proposition 4, all schedules with no idle time and no inversions have the same maximal lateness. Therefore, any schedule with no idle time and no inversions is optimal. The greedy algorithm produces a schedule with no idle time and no inversions. Hence, it is optimal and minimizes the maximal lateness. Finally, we analyze the time complexity of the greedy algorithm. In line 2, sorting the jobs by deadline takes O n log n time. The for loop in line 4 processes each job once, which runs O n iterations. All other operations run in constant time. Therefore, the overall time complexity is O n log n, dominated by the sorting step. In summary, we presented a greedy algorithm for the minimized maximal lateness problem. The algorithm follows the earliest deadline first strategy and runs in O n log n time. Thank you for watching and see you next time.